Hi, good afternoon, everyone. So I'm going to teach you about Einstein's general relativity, which is ultimately a model that allows us to understand gravity in a more general sense and ultimately allows us to understand how light can be bent by gravity, which explains black holes. So let's jump right into it. According to Newton, so if we take our Newtonian concept, the force of gravity only acts on objects with mass. And it is well known that light has no mass, so can a beam of light be bent by a gravitational field? On one hand, you should say no because light has no mass, but it turns out it can. And that's where we want to explain an alternative view of gravity using the idea of warp space. So what we're going to do are some scenarios involving different frames of references where one frame we're inside a room, an elevator that you can't see out of, but you can see into. And we're going to compare what two different observers see, the person on the inside and the person on the outside. We're going to do two different sets of scenarios that's going to ultimately lead us to understand how we can explain how we bend light. Okay, so our first case, we have this large room, windowless, it's hoisted on a tall crane, person on the inside with a ball, but they don't know that they're hoisted on a crane. They just think they're inside a very large room. We could expand that room to be as big as we want. It could be a whole universe where they are stuck inside that universe, that world, whatever you want to be. And then we have a person on the outside who can see in through cameras and whatnot. So like a big brother, if you will. So let's say there's an event. The event is this ball is let go. All right, so what does person P see? Person C is the ball drops, accelerates. I'll just say drops. And what does person O see? The same thing. We both agree. And if we ask why did the ball drop, why did it go from moving to accelerating? Because of gravity. Okay, so we're just using this for a contrast. So both frames agree that some force is pulling that ball down. And the reason they agree because both frames of reference aren't moving relative to each other. Okay, so you can't distinguish. There's no reason to tell a difference between them if you're in the same, essentially same frame of reference. Now we're going to change things. So in situation 2, we're going to cut the cable so that from our vantage point, this whole thing goes into free fall. So again, the person who doesn't know the cable is cut because that's outside their universe, outside their world, outside that elevator, releases the ball. Okay, what does P see the ball doing? Well, even though person P doesn't know this, they and the ball are both accelerating along with the room or the elevator at the same rate. So when they let it go, the ball hovers, if you will, in front of him or her. Hovers / floats. Okay, O sees, the ball falling with the person and the elevator. So let's talk about why. Well, I'm not going to write it down for O, but O would say this is simply occurring because the whole system is falling due to gravity. But P on the inside, who can't see what's on the outside, doesn't know the cable is cut, is going to say, hey, the ball is floating in front of me. So they're going to say, oh, there's no gravity. In other words, gravity was somehow turned off. So A says, no, it's an accelerating frame, if you want the specific term, accelerating world. I mean, just instead we use the word frame, the world. That person's whole world, which is contained inside an elevator, is simply accelerating. They say, no, there's no gravity. And here's the key thing. What's the difference? Or who's right? The answer is they're both valid. You cannot distinguish between the two. It depends on your frame of reference. So here we see for the first time that the absence of gravity is similar to being in a freely falling frame. You can't distinguish between the two. When we talked about that with astronauts in the space station, that's exactly what they experience. Okay, now let's change things. Now we move into, take that world and put it in the absence of a gravitational field. In other words, let's say they're in the middle of outer space. There's nothing nearby pushing or pulling on them gravitationally. And then we have person O who is hovering outside that universe, maybe in a spaceship just watching it, or they could be on their own planet watching from afar with a camera. Anyway, the first scenario, they're not moving relative to each other. In other words, this thing is just hovering at the same motion with this. So P lets go of the ball and O sees the ball, and they see it both floating. Okay? And why? They'd both agree, no gravity. Okay, there is no object, no planet nearby or star nearby that's making the ball fall. The elevator is not going to pull it down on its own, so it just floats around. Now, we change the situation. We do the exact reverse as the one above. Some mother spaceship or spaceship comes along, attaches the cable to this, and not just pulls it up, but accelerates it up. Okay? And just as this elevator is accelerating up, the person drops the ball. What is the person going to see the ball doing? Sees the ball fall to the floor. Okay, make sure you understand why that is. What does O see? O doesn't see the ball fall to the floor. O sees the floor rise and hit the ball. Okay? In other words, they say the ball hit the floor because we have an accelerating world. That's the elevator. This person says the ball fell to the floor because there's gravity, where there once wasn't a few minutes ago. Let's put F of G. Okay? They have no idea that something is going on outside their world that's accelerating them up. They can't see outside their world. So what do they feel as that acceleration? They feel a heaviness, a force of gravity that wasn't there before. And that's kind of what we experience in the elevator, how you can be made to feel heavier, not because you have more mass or there's more gravitational pull, but because you're accelerating up. And again, who's right? Is there really because of gravity there now, or is it just because it's an accelerating world? And the crucial thing is they're identical. It depends on your frame of reference. You can't distinguish one from the other. So you might be tempted to say, no, it's really falling because of that. But that's assuming you're outside the world. If we had a bunch of scientists, physicists, whatever, in that same world, they would say, oh, gravity suddenly turned on. We're not quite sure why, but it did. So that leads to a very important thing called the Principle of Equivalence. No experiment can be performed that can distinguish between a uniform gravitational field and an equivalent uniformly accelerated frame of reference. And that I was using the word world in those situations. So let's turn our attention to see why then we can say gravity can bend light. All right, so this is going to be maybe a little bit difficult to follow. Do your best. But let me explain the situation. So what I have is an elevator, and I've shown it at 3 different times. Okay, so it's not 3 different elevators. It's the same elevator as it accelerates up. Okay? And so we're going to look at it again from the inside or from the outside. And another aspect of this, instead of the ball falling, we have a beam of light right there. So we've got a light beam that is going to travel across the elevator. Now, see if this makes sense. The light beam, there is no gravity, so we're in the middle of outer space, right? So what would we see? We would see the light beam just move in a straight line. It would move in a straight line, and I'm just going to draw all the way through like that. Again, those are not 3 different elevators. So if you are in the elevator, okay, I'm sorry, so what we would see here is the light beam starting here, and then by the time the light beam gets across the elevator here, the elevator has moved up, so it hits the elevator below where it started, which is what this black mark is. So let me say that again, because that's the crux to understanding this. What we see on the outside is the beam of light traveling in a straight line. There's no reason why it shouldn't. So it started here, but as the elevator goes up, the beam isn't carried with it. The light source is, but the beam itself is not affected by the accelerated elevator. So the beam keeps going in a straight line, but again, the elevator is moving up at the same time. So if the beam started high, or essentially at this height here, it's going to hit below right there. Okay, so from outside the elevator, we can understand that. But what if you're inside the elevator? If you're inside the elevator, you saw the light start here, or actually start here, and it ended up here, and in the between this time and this time, it bent. And what do you feel as the elevator is accelerating up? You feel like there's a gravitational field. So you say, why did that beam bend? Because gravity made it bend. We said, no, the beam never bent. It just hit below a lower spot because the elevator was accelerating up. So O sees the beam move in a curve. I'm sorry, my bad. I'm talking about P. Move in a straight line to a lower point opposite wall of the elevator, where P sees the beam bend under what he or she assumes to be the influence of gravity. And again, who's correct? They're both valid. So from the principle of equivalence, since both observations are correct, it is perfectly valid to say gravity can bend light. And so that's a cool way of doing it. So when I show you, or have showed you, that fabric of space, what we're really seeing is when you place a mass in space, it accelerates space towards it. Okay, towards that center where the mass is. So if you are in that part of space that is accelerating towards it, you will say, oh, there's some force of gravity pulling me inward. Whereas if you could step outside that universe, you would see yourself accelerating in because space itself is accelerating in. And that's that warpage type of things. Okay, now this leads to a very, very, very subtle, another fact. The principle, it leads to an important concept. It stems from the fact that there are two fundamentally different ways of measuring mass. Okay, as an AP and IB student, you are expected to know this fact. So when we talk about mass, or when we measure mass, okay, most often we measure mass, let's say using a scale or a balance, is its response to the force of gravity. In other words, if I place a mass on just a balance and it upsets the balance, I need to place another mass on the other side to balance it. But that only works if there's a gravitational field. If there's no gravity, mass isn't going to push down on the scale to make it tilt one way or the other. And so when you measure mass in a response to gravity, you are measuring what is called gravitational mass. And the equation for gravitational mass, I'll call mg, is nothing more than our second law of motion. It is the F of g divided by g. Okay? Which, if you rearrange that, that's just F of g equals mg. What this is gravitational mass. So instruments that use this, like I said, are electron or scales. Let's see. What do I want to say? Force scales or spring scales, I'm sorry. Okay, or beam balances. A spring scale doesn't stretch when you hang a mass on it unless there's gravity there. But what if we have the case where you are in a gravity-free environment, such as an astronaut in orbit, that even though technically there's gravity there, they feel like there's no gravity at all? How do you measure the mass of something? A scale or balance is worthless because they're not going to tilt or stretch a spring because everything's in free fall. So in this case, you must measure the mass of an object in response to a generic force. In other words, something other than gravity. And the more mass you have, that's more inertia, the less response you're going to get. So less response and more mass is the law of inertia. So that's called inertial mass. And the inertial mass is governed by the second law. So I can just say just the mass inertial is any generic force divided by the acceleration you get. So it's really the same version of this, but this is particular to gravity. This is particular to any other force. And so in space, what you can act as a force is a spring. You can have springs work perfectly fine when there's no gravity. Okay, if they go side to side, if you stretch a spring, it'll spring back whether there's gravity or not, and how it moves back and forth can be used to find mass, and this is called an inertial balance. I'll show you inertial balance in class, because we're going to do a lab with it eventually, okay? So inertial balances vibrate back and forth, and the mass of the object in question affects the period. We can measure time associated with that back and forth, and the relationship between is known. Then you can use the unknown mass, can be determined by the period. So to sum up, interesting enough, these two definitions of mass are completely independent of each other. Yet no experiment that we've ever done has shown them to be different. So experiments say inertial mass, for a given object, inertial mass and gravitational mass are identical, but there's no theory that says they have to be. And because of that, you get this weird effect of gravity that can bend light.